Hey everyone, today we're solving a classic stress transformation problem 7.61. We're given a specific state of stress and our goal is to find the range of angles theta where the transformed normal stress stays equal to or less than 50 megapascals. As we can see in the x-axis, we have tension, which means that is positive 90 megapascal. And then we see that our shear stress points clockwise on the right face, which means that we have a negative 60 megapascal and there's no vertical normal stress. So we mark it down as 0. Okay, now that we've listed our knowns, we will calculate the average normal stress, and we use this equation over here because it finds the baseline center point of our normal stresses, which is basically the constant value that our transformed stresses will fluctuate around as the element rotates. We plug in our known values that we have over here, and we get 45 megapascal for our average normal stress. Next, we calculate the radius value, r, which is given by this equation over here. And we use this specific equation because r represents the absolute maximum variation or amplitude of our stress state. It tells us the maximum possible swing of our normal stress above and below that 45 megapascal average. So we know this, so we plug it in, and we also know this, and we plug those in and we get 75 megapascals. Now we need a reliable starting anchor point, so we look for our principal angle, theta p. That's what the principal angle is. We use this double angle tangent formula because it locates the exact physical orientation where the normal stress reaches its absolute maximum peak value. So this is the equation over here. We plug in our knowns and we end up with minus 4/3. And if we take the arctan of that, we get minus 26.54 degrees. Our target limit for our transformed normal stress in the x-axis is 50 megapascal as given in the question. Because stress transformations follow a harmonic wave pattern, we can use a basic cosine trigonometric ratio to figure out our allowable deviation angle f. This tells us exactly how far we can safely rotate away from our maximum peak before the stress drops to our 50 megapascal limit. So we use this equation over here. We plug in our knowns that we just calculated, and we end up with phi equals to 43.0.9 degrees. Because the stress wave is perfectly symmetric, the normal stress will hit exactly 50 megapascal at an equal angular distance to the right and to the left of our peak principal plane. So we combine our angles to find the exact boundaries. So for our first boundary, theta h, we will have our principal angle plus the phi that we just found, and that gives us 16.52 degrees. And for a second boundary, theta kappa, we use our principal angle minus the phi. So since standard notation prefers positive angles between 0 to 180, we add 180 to our negative result to find its equivalent plane, which gives us 110.34 degrees. Any angle trapped between these two boundaries keeps the normal stress at or below our 50 megapascal threshold, and because a 2D state of stress repeats every 180 degrees as the element spins, we just add 180 degrees to our limits to get our second valid region. So our final ranges are 16.52 to 110.34 and 196.52 to 290.34. And that is the physical and mathematical reasoning behind the solution. Thanks for watching.